Okay, this video is all about the various confidence intervals that go along with linear regression. There are two goals for regression. The first is to perform a hypothesis test to determine whether or not a relationship exists, and we covered that in the previous video. Second, if a relationship does exist, then we would like to use it to analyze the relationship and make predictions about the y variable. The key thing to remember from the last video is that we can find the mean expected value of y for any given x value by plugging it into the best fit line. But this by itself isn't very satisfactory. This is equivalent to finding x bar in a one sample problem and then stopping and saying, I hope x bar is close to the population mean. It is much more insightful to build a confidence interval around that point. And there are two different confidence intervals that we can make in linear regression. We can make a confidence interval for the mean value of y, given any x value. This is much like confidence intervals that we have made in the past. Or we can make a confidence interval for an individual y value, given any x value. This kind of interval is called a prediction interval. I'll get into the similarities and differences of these intervals soon. We're going to use the pizza sales data again as our example. The complete data set is shown on the left, and I just need to remind you of the sample mean and variance for x, and here is the sample mean and variance for y. And lastly, here is the sample correlation and the best fit line for the data. These numbers will routinely pop up in the calculations, so take note of them. We also need some of the ANOVA table, so I've included it here. In particular, we're going to need the MSE. So take note of this number. Excel calls this row residual. I called it error in the last video. It's the same thing. And we're also going to bring along its degrees of freedom, 8. Before we get into the confidence intervals, there's an intermediate step that needs to be done. This step is unique to regression, and it comes from the y variable's dependence on x. We need to calculate something called leverage. The notation for leverage is usually h, and it is a function of x. It depends on sample size, x bar, and the sample variance of x. Let's plug in all the numbers, and we have a function of x. So if I were to say find the leverage when x equals 10, then we would simply plug 10 into the equation like that. Next, I want you to notice that this function is a relatively simple one. It's quadratic. If we graph leverage as a function of x, we can see the familiar parabolic curve. And because of the way the equation is written, we can see that the vertex point, the minimum point on the curve, is located at the point x bar, comma 1 over n. So leverage is smallest when x is equal to x bar and gradually gets larger as we move away from x bar. Okay, now it's time to start making confidence intervals. We'll start with the interval for the mean value of y. And in this particular example, we're going to find the 95% confidence interval for the mean value of y, given that x is equal to 18. Remember that student population and pizza sales are both measured in thousands. On the left, we see the basic one sample confidence interval for the mean. We're just going to replace the sample variance, as we so often do with the MSE, and we're also replacing 1 over n with the leverage. Otherwise, it should look remarkably similar. Our MSE had 8 degrees of freedom in the ANOVA table, so that comes along into the calculation. Next, we need to find the predicted value of y and the leverage when x equal to 18. We use the best fit line to find the predicted value of 150. This number is called y hat in the formula, and the leverage when x is equal to 18 is 0.128, and this number is called h. Let's plug in all the numbers into the formula. With 8 degrees of freedom, the middle 95% of the t-distribution is between plus and minus 2.306, so that is our t-value. You can verify that in the t-tables. And we end up with this interval. Notice that the center of the interval is the predicted value of y from the best fit line, given our x value. So we are 95% confident that the mean pizza sales for all towns with 18,000 students is within this interval, or $150,000 plus or minus $11,400. We have the confidence interval for the mean value of y, but that's essentially the same thing as the line defining the relationship between x and y. We can use a computer and really take this to the next level. In this picture, I used Excel to literally make hundreds of confidence intervals between x equals 2 and x equals 26. So instead of just one interval, I have something like a confidence tunnel, although the book would prefer to say confidence band. It is more or less fine to think of this as the 95% confidence band for the true linear relationship between x and y using beta 1 and beta 0. So we are 95% confident that the unknown linear relationship between x and y lies within this band. I also want to point out that the upper and lower confidence limits don't exactly form straight lines. This is entirely because of leverage. We can see that the confidence interval is smallest at x bar, or 14, because this is where leverage is at its minimum possible value. As we move farther away from x bar, then the intervals get noticeably larger. And this is all because of leverage. And even though it is very shallow, we can see a slight bend due to the quadratic leverage function. Next, we're going to move on to the prediction interval. That means we're going to make an interval for one individual y value, something we have never done before. In this example, we're going to make the 95% prediction interval for an individual y value given that x is equal to 9. The formula for a prediction interval is very similar to the confidence interval for the mean. The only change is to add 1 to the leverage. Let me try to explain why this makes good sense. The mean of y is unknown, and the previous formula showed that it has an estimated variance equal to the MSE times the leverage. On top of that, we also have the variance of an individual point, which is estimated by the MSE alone. We have to add the uncertainty of the mean with the uncertainty of a point to get this total variance inside the square root. Anyway, to begin this example, we need to find the predicted value of y from the best fit line and the leverage when x is equal to 9. Plugging in x equals 9, we get a y hat equal to 105 and a leverage of 0.144. Let's plug these numbers into the formula. The t-value is exactly the same as before, since we have the same confidence level and we still have 8 degrees of freedom from the MSE. So we are 95% confident that the pizza sales for an individual restaurant in a town of 9,000 students will be within this interval. The prediction interval applies to individual values of y, so it's all about individual points. Once again, I have used a computer to make hundreds of prediction intervals to create this confidence tunnel. The first thing you'll probably notice is that this tunnel is much wider than the previous one. That's because the variance is much larger in this formula. In fact, the variance is so dominant in the calculation that it's harder to see the parabolic curve of the leverage. It's still there, but it's just overwhelmed by the other numbers in the calculation to the point that it's difficult to even notice it. Next, I want to emphasize that this is the confidence band for points. So we are 95% confident that any point will be within this band. All of our data points happen to be within it, but that of course won't always be the case. It's possible for points to be outside of the band. It's just unlikely. There is one more interval to consider, and that is the confidence interval of the slope coefficient of the line. This comes directly from the t-test in the last video, so it does have some usefulness after all. The first step is to find the middle area of the t-distribution, and this depends on the confidence level and degrees of freedom. Next, we just need to solve for beta 1, the unknown slope coefficient, in the middle of the inequality. This is a process we've done plenty of times in the past, so the math should be familiar. And we end up with this expression. The best fit line slope is the center of the interval, and the half width is the t-value times the standard error of the slope, which I have abbreviated as SE. Let's find the 95% confidence interval for the slope. The best fit line slope was equal to 5. The degrees of freedom are still 8, so we have the exact same t value as before. And the standard error, after you plug in the numbers, is equal to the square root of 0.3367. This works out as 5 plus or minus 1.338, or this interval here. This interval is actually given in the regression computer output shown much earlier in this video. Here it is again. In the bottom row, we have the best fit slope coefficient. Its standard error, its t-test information, and then finally its 95% confidence interval. So all this information is given for free in the usual Excel output. Next, I want to do a fairly common application of the slope confidence interval. I want to make the 95% confidence interval for the mean change in y given an increase of 4 in x. This is actually pretty simple. All we need to do is start with the 95% confidence interval for the slope coefficient, and remember that this is the interval for the mean change in y for an increase of 1 in x. In order to adjust this for a change of 4 in x, we just need to multiply the interval by 4. So we are 95% confident that an increase of 4,000 students will increase the mean pizza sales by between 14,648 and 25,352. Just remember that the line represents mean pizza sales, not individual restaurants. Finally, here is data on 14 companies. The X variable is its market cap, measured in millions of dollars, and the Y variable is its CEO's salary, measured in thousands of dollars. And over here on the right, I've given you lots of useful information, including the error sum of squares from the ANOVA table. So copy this down, since you'll need it to answer the 3 questions coming up. Good luck with that, and check out the next video.